In this lecture, we will look at the small signal voltage gain of common emitter fixed bias amplifier. So we are going to perform small signal analysis of this particular common emitter amplifier, which is provided with the fixed biasing through the resistor RB from VCC DC voltage source. Here Vs is the input signal, Vo is the output signal, II is the input current, IO is the output current, C1 and C2 are the blocking capacitors. Now if you were to perform the small signal analysis for this particular common emitter fixed bias amplifier circuit, you need to remove the DC effects of VCC by short circuiting the voltage source, and you need to replace the blocking capacitors C1 and C2 by short circuits. For example, the impedance offered by a capacitor is given by the expression Zc is equals to minus jXc, where Xc is equals to 1 by 2 pi Fc. Now substituting the value of C and F, the value of Zc will be very small. Therefore, you can comfortably replace the capacitor by a short circuit for performing signal analysis. What I mean to say is, for a signal voltage which is having a definite amount of frequency, the capacitor C1 and C2 can be replaced by short circuits. Now we are going to perform small signal analysis for this particular amplifier. Now, as I have said previously, we are going to remove the effects of the DC voltages. This can be done by shorting or short circuiting the voltage sources VCC to ground. So now if I short this, so I am pulling it down to ground. Now this node, when it is put to ground, the resistor RB is also from base terminal to the ground, which I have represented here. Now this is the small signal network for performing the analysis. Take for example, for this particular amplifier circuit, I can find out the input impedance offered to the signal, the output impedance ZO, and the gain of the amplifier, which is VO by Vs. Now, the bipolar junction transistor is represented by equivalent RE model into the network, which we have seen earlier in the previous classes, where the input side of the bipolar junction transistor is represented by a resistor whose magnitude is beta Re, and the output is represented by a current source. Here, this is a current source whose magnitude is dependent on the input base current. And we are also taking into account the early effect, which is represented here in the form of a resistor whose value is R0. And RC is the collector resistance. What exactly we are doing here is, the bipolar junction transistor is replaced by an equivalent RE model. Well, now this is the input circuit and this is the output circuit. Now if you look at the input circuit, the input impedance is nothing but the parallel combination of RB and beta Re. The input impedance is nothing but the parallel combination of RB and beta Re. The value of RB is greater than beta Re. Usually, if it is greater by a factor of 10, then the input impedance of the circuit is nothing but beta Re, the parallel combination. the equivalent resistance will be lesser than the smaller resistance value. Therefore, the input resistance Zi is nothing but beta Re. Now, we will calculate the output impedance Z0 of this particular C fixed bias amplifier. Now, how do you calculate the output impedance? Now, to calculate the output impedance, the signal source has to be set to 0. Now, in this particular circuit, if I make Vs 0, then there is no current at the input. II is 0. If II is 0, obviously IB also is 0 at the input side. If IB is 0 at the output, then the magnitude of the current source is nothing but beta times 0, which is also 0. Obviously, there is no current flowing here. Therefore, the current source is represented by a open circuit here. That's what you are seeing. Now, the output circuit is left only with R0 and RC, which are in parallel. Therefore, Z0 is equals to the parallel combination of RC and R0. Suppose if R0 value is greater than RC by 10 times, in that case, then Z0 can be written approximately equal to RC. If R0 value is greater than or equal to 10 times RC, in that case, Z0 is approximately equal to RC. Now we will look at the derivation of the voltage gain AV. The output voltage V0 is equals to the current flowing in the parallel combination of R0 and RC. Now if you happen to see, the current beta IB is flowing into the equivalent circuit formed by the parallel combination of R0 and RC. We also know that IB is equals to Vs by beta times Re. From these two expressions, rewriting them and appropriately substituting them, output voltage V0 is equals to minus beta times Vs by beta Re multiplied by the parallel combination of R0 and RC. Now, the signal voltage gain is nothing but the ratio of output voltage to input voltage Vs. Therefore, AV is equals to V0 by Vs, which is nothing but the parallel combination of R0 RC by Re with a negative sign over there. If R0 is greater than or equal to 10 times RC, then the signal voltage gain AV is approximately equal to minus RC by Re. Now the negative sign here indicates that the output and the input has a phase shift of 180 degrees among them. Thank you.